transfer project was on how stress tests affect the bioluminescence produced by a species of bacteria known as Parasittis lunula, aka known as Parasittis fusiformis. In an age that relies on technology to thrive, bioengineering has become more popular than ever. However, light pollution is skyrocketing, and with up to 3.3 billion being wasted on unshielded lights, a renewable source of light would be groundbreaking, such as bioluminescence. However, not much is known exactly in how said phenomenon works. What are its advantages or downfalls? What kind of stress could it take? By recording how bioluminescence-producing dinoflagellates react to different levels of light exposure, their efficiency can be measured. One guess could be that when not given any light at all, the bacteria would suffer as a result. After putting bacteria cultures through light-related alters to their environment, this conclusion was produced, nearly killing the culture kept in the dark. My hypothesis for this project was if light levels stay in constant darkness, then the bioluminescent dinoflagellates will have a harder time producing bioluminescence due to a significant lack of light for it to photosynthesize. To set up this experiment to figure out if this would work, of course, I needed my 3 culture jars, being Dinoflagellate Parasittis lunula, aka Parasittis luciformis, and a heating lamp, specifically a Zoomed Represent 5.0 UVB self-ballasted lamp, 13 inches away from the specimens, 2 cardboard bags, and a 20-gallon reptile tank to keep the specimens in safely. The methods will be explained along with the procedure. To test how bioluminescent bacteria reacts to different levels of light exposure, the bacteria must first be set up in cultures. These will be in 6 identical test tubes, which were whittled down to 3. The tubes will remain sealed, and the temperature must be regulated to stay around room temperature, or 65 to 75 degrees Fahrenheit, aka 18 to 24 degrees Celsius. 2 of the 6, well, 1 of the 3 in this case, test tubes will be labeled light and kept in direct light exposure at all times. Another one will be labeled dark and will have their tubes kept exclusively in the dark. The last 2 will be labeled light and dark and will be kept in darkness in the period of light and will be kept in light in the period of darkness. Basically, be kept in light overnight and be kept in dark over the day. Each set of tubes will be taken out and studied periodically for observations in a dark room. The methods for how this works. First, a basis must be set in order to vary the environments of the cultures, thus it'll act as an anchor to show what's normal bioluminescent reaction, what isn't. This requires letting the Parasittis lunula wake up and adjust on its own. Next, the specific alterations in each culture will be enforced. This will cause the deviations to surface for the nature of these stress tests, being light exposure and either overexposure or lack thereof. The cultures will be left to develop in their new conditions and frequently checked on to see if the disturbances caused any effect the production of bioluminescence. The dark light culture will be swapped between darkness and light at 9 o'clock intervals to emulate a day and night cycle. So the data and results we got from our tests. Data will be measured in a glow intensity chart ranging from 1 to 4, which was sketched in monochromally. 1 being lightest, 4 being darkest. And the unstressed bias basis here is 1. So day 1 produced, dark light produced a glow of around 1.8. This is being told by eyes, luminometers are not available. Dark produced 2.6, and light produced the basis being 1. However, in day 2, there's 3 different measurements, and each of them were wildly different than the last one. Dark light produced, at 6 o'clock, a 0.9 measure. It got better. Dark produced a 2.9 measure, meaning it got worse. And light produced a 1.5 measure, meaning it also got worse. At 7 o'clock, it was measured again, and dark light seemed to remain the same throughout. Dark got worse to a 3.
Do you want to get the animal and give it to me? You're decided to have it out. Okay, go.
Yep.
Hey, Lizalfos. Ow.
And light was pushed to 1.7. At 8 o'clock, like I said, dark light remained stagnant. Dark also remained at 3, and light got a little worse at 1.9. In day 3, we did the 6 o'clock, 7 o'clock, 8 o'clock tests again, and at 6 o'clock, dark light produced 0.8 and has produced 0.8 throughout. Dark produced 2.4 at 6 o'clock, then 2.5 at 7 o'clock, and then 2.4 again at 8 o'clock. However, the light produced at 6 o'clock produced 2.5, which is much worse than before. At 7 o'clock it produced 2.6, which is the worst it gets. And then at 8 o'clock it remains at 2.6. Now, the discussion, made from these results. The experiment resulted in a bit of a predictable set of results. The light and dark samples performed worse than the basis, but in an unexpected twist, the dark culture started faring better than the light one. These findings will hopefully be useful to those looking into researching bioluminescence to forge a path for a better tomorrow, as there's many studies out there hoping to make this biolight a renewable source of light for us to use. Now then, the stress test in question gave us a mixed set of data. The suffering of the dark culture helped create the conclusion that the cultures could not thrive well in extended periods of darkness, backed up by how they required light to photosynthesize. A certain piece of the results is more interesting, however, being that the light culture started suffering after extended periods of light exposure. Something was keeping them from glowing. There are limitations to how accurate the results are due to a lack of a luminometer to directly measure the bioluminescence itself. The conclusions from this, in a bolded format. The dark culture suffered the worst under its conditions. Light culture started off decent, around healthy basis, and declined over time. The dark light culture prospered. The hypothesis ended up being supported, making one able to assume it's true. The darkness stress test caused the most damage, reducing the amount of bioluminescence produced. A lack of luminometer restricts exact data. More tests to ensure accuracy would be preferred. And these results are part of an ever-compelling study in biolight and what influences it, starting with something as simple as the ocean's fireflies, Parasiticus lunae. An application to this. Despite being able to reach a conclusion, the results are to be assumed, as only a few tests were conducted. A larger pool of tests would be preferable. It could result in more findings than anticipated on how the organisms react and potentially adapt or suffer to their environments. Perhaps even adding another factor, variation, to produce newer results to see how that also affects bioluminescence would be preferable. Should one want to look into how to make a big difference in the world, a renewable light source is potentially one of the most essential things we need. And that's pretty much it.
And what about your examples?
My examples?
Yes, we're going to shakies.
My examples. And now we will show, hopefully,
over here though,
how this goes.
Turn that light off. Okay, good.
So,
ready? Which one is this one?
Will end up in camera, but this is the dark light one.
All right, this is the dark light combo.
This is the dark light combo. Yes.
Ready? Go. Shake. There's little glitz of, there we go. Little glitz of light.
After a while, they stop producing their stress light. But
okay. What's the next one?
That was the dark light.
That was dark light. What's the next one?
Then we have 100% light.
Okay. Ready? Shake. Not much of anything at all. I got nothing reading on my camera. Okay.
And last but not least, the 100% dark.
Nothing at all.
And that concludes this science fair experiment.
Okay, now take the lizard back.
I'll take the lizard back.
Say bye, Lizalfos! Oh, he's very cute. He wants to go back in his cake, though.